Determining magnetic field strength in unconstrained space requires a Biot-Savart integration, which sums the vector contributions from every differential segment of a current-carrying source. Ampere's law shifts the analytical focus, relating the magnetic field along a closed path specifically to the net current piercing the area that the path encloses. This relationship is defined by the circuital law equation. The left side of the expression is a line integral. It calculates the dot product of the magnetic field vector, B, and the infinitesimal displacement vector, dl, around a complete closed circuit. On the right side, we find the permeability of free space, multiplied by the enclosed current, represented by the variable I sub e. To apply this equation, we must establish a precise definition for enclosed current, address a common technical error regarding the total magnetic field vector, and maintain a rigorous sign convention for complex multi-lobe paths. In practice, Ampere's law functions as a topological counting exercise, where the geometry of the boundary is the primary factor in determining the final value. Consider this scenario: an arbitrary Amperian loop drawn through a region containing several independent current-carrying wires. We first apply the principle of exclusion. Currents I4 and I5 are located outside the physical boundary of our integration path. External wires do not pass through the loop, so their contribution is zero. We focus on internal currents, I1, I2, and I3. Summing these requires a sign convention. We assign a direction to the integration path, here counterclockwise. Using the right-hand rule, curl your fingers in the direction of the integration path. The thumb points out of the page. Current flowing in this direction is positive. Current flowing inward is negative. Based on this orientation, I1 and I3 are positive, while I2 is negative. This yields an enclosed current of I1 minus I2 plus I3. The final enclosed current is an active calculation determined by the chosen direction of the integration boundary. This raises a question. If the positive and negative currents within a loop sum to zero, does the magnetic field itself disappear? The technical notes specify that the variable B represents the total magnetic field at any point on the path. A common misconception is that if the global integral evaluates to zero, the local magnetic field at points along the path must also be zero. Imagine an empty circular loop placed next to a high-current wire that remains outside the loop's boundary. The external wire generates a magnetic field that physically intersects the path of the empty loop. In Ampere's law, the B vector accounts for every magnetic field present at that coordinate, including those from sources outside the loop. As we integrate around the loop, the dot product of the field and the path element produces positive values on one side of the circle and negative values on the opposite side. The integral of an empty loop evaluates to zero because the external magnetic field vectors align with the path on one side and opposite on the other, creating a numerical cancellation over the full circuit. We can apply these principles to a self-intersecting path that encloses several disparate currents across multiple lobes. We evaluate each lobe sequentially. Lobe 1 is counterclockwise. Its outward current means positive I. The path crosses, making lobe 2 clockwise. Outward current here is negative I. Lobe 3 is counterclockwise, with inward current, negative I. Lobe 4 is clockwise. Outward current gives negative I. Summing these individual lobes results in positive I followed by 3 negative I values, for a net total of negative 2I. Multiplying by the permeability constant completes the integral. The final result of negative 2 is a direct consequence of how the alternating geometry of the path interacts with the current directions. This complex calculation demonstrates the consistency of our analytical rules. First, the boundary is the sole determinant of enclosed current. External sources have no impact on the final integral value. Second, the total magnetic field vector at any point on the path accounting Arnold's forces, but the closed-loop integration process filters out external interference through cancellation. Third, sign convention is entirely dependent on the local direction of the path. We must apply the right-hand rule lobe by lobe to ensure accuracy. When we prioritize these boundary definitions and local sign conventions, the complexities of spatial field interactions resolve into a series of predictable, discrete steps.